So now let's look at the slides I had shared with you before, and there are a few things I want you to pay attention to. I mean, let's first a recap of everything we said so far. So this was the brick and mortar structure that we investigated a lot, and this is the building block that we investigated. Now, back when we started this conversation, I pointed out three examples of biological materials. I told you about these beta sheets with hydrogen bonds. I told you about these protein polymers and that are interacting with hydrogen bonds. I also told you about this abalone shell, the building block, which is truly um, uh, the this brick and mortar, hands down, undeniable. I mean, it's a and these are real engineered, real biological materials. Three different length scales. So now, look at this graph here. The three are shown here, and I'm showing you two uh, uh, points at every for every structure. One is the experimental data, the length of the constituents here, the size of the constituents and the overlap length, basically L star and L double star. Okay, so L star and L double star are drawn here, and constituent size is drawn there. When we talk about experiments, for each constituent, we know the length, so it's only one length, but there's a variability in nature. In the model side, the range is based on L star and L double star, so the range includes both of them, and you see the overlap between all three. So basically, from here, we can conclude that the nature, what one design element we can take from nature is that it's choosing the size of the constituents, especially the length, for instance, for a given material, for a given set of material properties that comes from the constituent properties, to maximize the elastic energy density, so that the critical elastic energy density, so that it's basically the ability of the material to absorb as much energy as it can without failing. Also, when it goes to the extreme case that the load keeps increasing and increasing and increasing, eventually it starts to deform plastically, but it let the plastic region expand all along, and the length of the constituents is defined so that the plastic region can develop. So as a result of those, nature is maximizing the maximum load that the structure can, the interface can also take. And this combination, especially the ability to expand the plastic region, is truly amazing. I want to give you one example that it's, in my opinion, really breathtaking. The seashell, it's 95%. So let me bring my pen back. Where's my pen? It's here. So it's 95% a mineral, which is brittle. Okay, it's only 5% composed of this of the biopolymer. That it's a sophisticated set of materials. Sophisticated polymer. It's a very complex chemistry, but it's only 5%. Now, the toughness that you get out of this composite material is many times because of this brick and mortar structure that I showed you earlier, and the size of the components are set properly, the energy that it can dissipate before failure is many times higher than the energy that is required to just break the brittle material. So, and this is a clear example of setting the dimensions of the components right as a function of the material properties and certain length to scales that are present in the material. So in some sense, this is optimized based on a given set of chemistry and given set of properties of the constituents. So this concludes our lecture on bio-inspired materials, and I hope you have enjoyed this new mode of education so far.